Hi, and welcome back. We're still in the chapter of rotational motion. And if it feels like a marathon, it is. Usually, our author is pretty good at breaking down chapters into multiple, breaking down topics into multiple chapters. Like, for example, Newton's laws, he spent about 4 chapters on it. However, rotational motion, he's doing it all in one chapter, which is fine, but it's a longer chapter. So we're kind of in the last segment of this. So it's rolling motion. So let me show you. We have been doing rotations about a fixed axis. So you have a wheel here, and it just spins in place. It does not move. We call this a pure rotation. If it just moves without rotating, we call this a pure translation. If it rolls while rotating, then this is rolling motion. It could be rolling with slipping like this, if it's slippery or you accelerate really quick, or if you lock the brakes, you could be skidding. Okay. So we're going to look for motion at rolling without slipping. For example, you could have a ball and it's spinning. While it is spinning, it has rotational motion and translational motion at the same time. Same thing if you have a hoop here and you let it spin, it's rolling without slipping. And so it has also rolling motion with translational motion. And you will see that the kinetic energy will break down very nicely into a rotational part and a translational part. And that's what I want to do now. So the first segment or two of this will seem a little bit more mathematical, but try to follow them because the book kind of does it, but it's in a different way. So I want to do it slightly differently and then maybe also look back at the book's way and then talk about both of them. So the last segment of this chapter, also in the book, you got some cross products and so on. So it's more mathematical. All right, let's get to it. So the first part, I'm going to talk about rolling without slipping and how to identify it. So let's take our hoop or our wheel, something that could roll. So usually it's circular. So here is the x-axis. And suppose our wheel will start here. And it will make a turn. Our wheel will have a radius r. So initially it's right here. As it spins, as it rolls, a little bit later, let's call this here the x-axis. So when it makes a complete turn, it will be here. I hope these two circles are equal in size. It's supposed to be the same thing. So it gets here after a while. Right? It gets here. So by the time it gets here, how far did it move? What's this distance? Well, it's if you imagine you can paint this or something, if it rolls, every point has touched once and then it got to here. So it's equal to the circumference of the circle. So it's 2 pi r. So let's calculate the speed. The speed of this wheel, how fast is it moving to the right? Well, the speed is the distance traveled over the time elapses, so it's 2 pi r divided by the time it takes to complete one cycle, which is the period. Now, the angular velocity, which is omega, is how much angle you make per unit of time. If it spins by one turn, that's a 2 pi, and it did that over a time period, capital T. And so, for rolling without slipping, notice 2 pi over t is equal to omega, so it's equal to omega times r. So let's summarize this. So rolling without slipping slipping. The condition is that V is equal to omega times R. If V is not equal to omega times R, then it's either skidding or it's slipping. So let's define that. So if V is greater than omega R, or if V is less than omega R. Let's take two extreme cases. When V, let's take the first one. When V is less than omega R, what is this called? What do we call this? Go to your mechanic. The mechanic lifts the car and makes the car roll. What's the speed of the car? Well, the car is not moving at all. The wheels are spinning, but the car is not changing position, so its velocity is equal to 0. So in that case, omega R is not 0, but V is, so V is less than omega R. That's called slipping. That's when you kind of turn you hit the gas really quick and the wheels spin in place, and you make some smoke. That's called slipping. In the extreme cases, when you just slip and roll in place and not move at all. That's called slipping. And this is called skidding. If you're in your car, you lock the brakes so the wheel kind of stops rolling, but it's slipping. It's sliding, just sliding on the concrete or on the asphalt or on the ice. That is called skidding. Sliding, skidding or sliding, and this one is slipping. I just wanted to distinguish them. And this is what we care about, the rolling without slipping. That's the one we do. We're not going to use this. Okay, great. Now, I want to determine, I know the speed is V, but I want to determine how quickly each point on the circumference is moving. Because the center of mass is moving at a speed V, but this point it's moving to the right while turning. So you have rolling without slipping is really a combination of two things. It's a pure roll plus pure translation. Again, translation just means you move from one place to another, and roll, you just spin about the axis. So a pure roll, you just spin around the axis. So this point here will be moving at speed V, and this point here will be, because you're spinning like this, so this point will be moving back with speed V. And V is equal to omega times R, and here V is equal to also omega times R, but it's to the left. Omega R to the left. Here, if you're just pure translation, you lock the wheels and you move, both of these, this one will move at speed V, the center of mass moves at speed V, and this one will move at speed V. You lock the wheel and everything just, here is the wheel, everything just moves like this. That's called pure translation. This is a pure rotation, and the combination of the two is rolling without slipping. So if you add them, what do you get? Well, you get the center of mass here was not moving if it's pure rotation, and you add to it a V, so that's a V. This one you got a V to the right on top of a V to the right, so that's 2V, a V and another V, so that's 2V. And this point here is actually moving at 0 velocity because it's you got a V to the right and a V to the left, so that's 0. And I want to show you this in a more formal manner. So let's go to the next board. I will redraw this picture. Here's my X, here's my Y-axis. Let me take my wheel, or something that turns. So, and I'm going to trace one point, let's say this red point. As the wheel turns, so let it turn a little bit. Turn by an angle theta. So this point that used to be here has now turned, and let's say it's here, okay? It's there. That's where it is. So I want to know, relative to the origin here, the position of this point. The position of this point initially was 0 because it was at the origin. But a little bit later, its position is here. That's called R. That's R. So what is R? How am I going to find it? Well, first of all, how far is the wheel from where it started? It's here. It's here. And how far is this distance? Well, this distance, remember, if this is theta, then this is r times theta. Remember, it's just this length of this arc. This is r times theta. And this is capital R, the radius of the wheel. Just write it in. This is r. Okay. This is r, the radius of the wheel. And this is little r, the location of this red point. The location of that red point. I want to use r and then but I don't know how to, what is r in terms of the radius of the wheel and theta? We're going to write r in terms of the sum of 3 vectors. So, because how do you get to this point? Well, you can go through this vector, and then this way. You go to the right, and then straight up, and then this way. And I'm going to call this vector here vector A. Vector A. And how much is vector A? Well, vector A points in the x direction and it has magnitude r theta. So vector A is simply r theta I hat. And this thing here is vector B. And vector B points straight up. And how large is it? Well, it's equal to the radius of the wheel. So it's r and it's j hat because it's in the y direction. And then vector C here, this is vector C. Vector C is trickier because it has 2 components. One of them is in the x direction, the other one is in the y direction. The x component of this vector C, you see vector C points this way. It has magnitude r, because it's from here to here, but it has 2 components. One of them is in the x direction but backwards, and one of them is in the y direction and it's also downward. And this is theta. So if this is r, then this side here is the adjacent to theta, so it's r cosine theta, but it's downward. And this one will be the opposite to theta, so it's r sine theta, but it's to the left. So this one downward is negative, and this one is to the left, it's negative. So this vector C will be negative r sine theta in the I hat direction, negative r sine theta in the I hat direction, and minus r cosine theta in the y direction. So vector r will equal to vector A plus vector B plus vector C. That's what will get us there. So you can go straight to here, or you can go this way. But it seems more complicated to do it in 3 parts, but we know what those 3 parts are, and that's where we're using it. So the vector r is equal to vector A plus the vector B plus the vector C, and it is equal to what? Vector A is r theta I hat plus the vector B, that's r j hat, plus the vector C. The vector C is negative r sine theta I hat, negative r cosine theta j hat, cosine theta j hat. So the vector r, the position of that red dot that we're tracing, let's put the r's together, the I hats together. So I will factor an r. So that gives me theta minus sine theta I hat plus, now these two, factor the r out, and have 1 minus the cosine of theta and j hat. So that's the position vector of a point on the rim that started at the origin as the wheel started to rotate. That's the position vector. All right, If you know the position vector, you can calculate the velocity vector. Well, the velocity vector is dr dt. Okay. We have to take derivative of this. Notice theta is changing over time. Right? Theta was 0 and it's growing as you spin. So theta is a function of time. So when you take the derivative, you have to use the chain rule sometimes. So, but r, capital R is not changing. It's the radius of the wheel, so it's a constant. So let's take the derivative. So r, and then here I would have the I hat. Derivative of theta is d theta dt, d theta dt, and then minus. Derivative of cosine is, derivative of sine is cosine, so cosine theta, and then by the chain rule I have to take the derivative of theta, so that's a d theta dt, and then plus r times derivative of 1 is 0, derivative of cosine is negative sign, but there is a minus sign, there is a minus in front of it, so that becomes positive sine of theta, and then by the chain rule I have to take the derivative of theta, so that's a d theta dt, and you have the j hat. Remember, d theta dt is called omega, so this is omega and this is omega, so therefore v will be, this is omega, we factor it out, so we get r times omega times 1 minus the cosine of theta I hat, and then plus r omega times the sine of theta j hat. Okay? Okay, sounds good. Now, how fast is theta going? How fast is this point going? I want to show you that when the point is in the bottom, the velocity is 0. And when the point is on top, the velocity is 2v. On the bottom, theta is 0, or maybe it's spun by 2 pi, or maybe by 4 pi, and so on. So every 2 pi, it comes back to the bottom. So when theta is 2 pi, let's say, or 0, what is the speed? Well, let's see. Let me circle this because it's an important equation. By the way, this equation is called, this parametric equation is called the cycloid curve. You can look it up, cycloid. It traces a curve called the cycloid. It looks like this. All right, so what is v if theta is equal to 0 or 2 pi or 4 pi, meaning when this point is at the bottom? I expect it to be 0, so let's see. V, when theta is equal to 0 or 2 pi or whatever, I'll just put 0. When theta is 0, when it's at the bottom. Well, at 0, the cosine of 0 is 1, and 1 minus 1 is 0, so this part becomes a 0. If you like 2 pi, well, cosine of 2 pi is the same as the cosine of 0, and it's 1. 1 minus 1 is 0. 1 minus 1 is 0. So this part will be 0. How about this part? The sine of 0, or 2 pi, or 4 pi, or 6 pi is all 0. So this is 0, so you get a 0. So what's the velocity of the point when it's at the top of the circle? At the top of the circle, it means it turned by a pi. When theta is equal to pi, this point will be at the top of the circle. Or 3 pi or 5 pi. So when theta is pi, what do we get? Well, let's see. You get r omega. And then, what is the cosine of pi? Cosine of 180 is negative 1. And you have a minus sign, it becomes plus 1. And 1 plus 1 is 2, so you get 2 r omega I hat. Okay? And then plus, sine of pi is 0. So that part is 0. So the magnitude of v, when theta is equal to pi. Remember, for the magnitude, well, here you only have the x component, so it's just 2r omega. Equal to 2r omega. And remember, the center of mass is moving at omega r. This one is moving at twice omega r, so it's twice the velocity of the center of mass. So it's twice the velocity of the center of mass. So that's what I wanted to prove to you. So now you're convinced for sure that at this point, when the wheel is spinning and it's at the bottom, it is 0. And that's why it's also considered the friction here. There is no relative motion between this point, a point on the circle, and the ground, because the velocity is 0 when it's in contact. So it's static friction when it's there. Okay. The next thing I want to prove to you, to show you, is the kinetic energy of something that is spinning, okay, that is rotating and rolling. And I think I will need more than 10 minutes. This video will end in about 9 minutes. So let's pause it, stop it, and then start a fresh video to do rolling motion, and I will calculate the kinetic energy for that, and then show you how you get a very nice formula. All right, I'll see you in a moment.